Welcome back. We're at section 2.3, and for some of you, you've been waiting for this for the whole time. So, for those of you who know what's coming, we should have a little bit of a drum roll here. I'm not sure that I have one on my desk, or I'd be tempted to do it. Slope and rate of change. And we're talking algebraically as opposed to geometrically. We're going to use this three-step method. Remember, the four-step method referred to the difference quotient. I don't really stick with the 3 steps. I just do it. But that's up to you. Whatever works for you is what's important. So here's the derivative. Notice one thing, that the derivative is the function with an apostrophe on the f. So that tells you it's not just the function, it's the derivative of the function. Now, it's not a d up here or anything like that, just f prime, and when we're talking about functions, f prime means the derivative. And the way it goes is this. Some of this should look familiar, if not all of it. We've got f of x, the actual function itself. We've got the actual function itself, but with x plus h's, anywhere the x was in the original function. Down here, just h. We've got a limit as that h, that small positive number, approaches closer and closer to 0. And that's assuming that the limit exists. There are situations where the limit does not exist. Next, this is one way we describe the function. Another way, since f of x and y are the same thing, we could describe the function or the derivative as y prime. Another way we could describe it, since it's the derivative of y with respect to x, another notation that's seen quite often and can be quite convenient at times, especially when we get the differentials, is dy dx. That represents the derivative of y with respect to x. So we're taking the derivative of this function y, but it's with respect to x. If we've got any other variables, they're not changing. We're talking about changes in x. Here's a picture on the left. That's what we're talking about in general. 3-step method. First, form the ratio. Should know the plan by now. Get that difference quotient. Simplify it. That's usually the hard part, although sometimes it can be tricky. Make sure you put x plus h in for all the x's. Then you calculate the limit as h approaches 0, if it exists. Usually, especially in business applications, we don't have to concern ourselves with that too much, but we might keep that in the back of our minds just in case. Next, let's try it for this function. So, how do we solve it? First of all, put the difference quotient together. Remember, on the top we'll have the function with x plus h's where the x's were, and then we'll subtract the original function and put h by itself in the bottom. There's the general plan, and there are the x plus h's in function, where over here we just see the x's, and h is all by itself down in the denominator. But remember, h is not allowed to be 0, but we can get as close as we want. 0 point, and we can have 1,000 different zeros, and let's say there's a 5 at the end. Step 2. simplify it. A lot of algebra can go on here, especially if you've got fractions. In this case, the first thing we need to do is expand, multiplying this out with a -5, and also cubing this. Well, that can be tricky, so here's a tip up here. Here's a different kind of binomial. This is a binomial. You've got x, you've got h, two terms, it's a binomial. You can do it the long way. You can take a plus b times a plus b, finish that, and take it times a plus b again. Or you may choose, since the cube does occur occasionally, to remember this. To cube that, you've got a cubed plus 3 there because we're cubing. A drops down in power to 1. B goes from a 0 to a 1. Another 3. A goes from a cubed to a squared to a. B goes up 1. And b cubed at the end. This can be handy. Next, put all that together. Here's our expanded x plus h cubed. Here's our -5 times x plus h. And we're subtracting the original function there. And of course, our old friend h in the denominator. Some of those terms in the top cancel out, like the 5x, -5x and 5x give you 0, and so on. What you're left with is this. Next, factor out that h, or you could just divide this h into all 3 of those, which is the same as what we're doing here, and that's our answer for the difference quotient simplified. Now we apply the limit. Take the limit of what we just got from the difference quotient. Notice that what we've got inside the parentheses is a polynomial. And that's pretty nice, because with polynomials, all we need to do to find the limit is put 0 where the h's are. And what's left? All those zeros eliminate 2 of the terms, and we're left with 3x squared minus 5. That's our derivative. So the derivative, and remember this is the same thing as y prime, which is the same thing as dy dx, or the derivative of y with respect to x. Any one of those can be used to describe the derivative. Conditions. Sometimes things don't work out too well. If that function is discontinuous, in other words, if you were drawing it, you'd have to lift your pencil or pen to actually draw it, then it's not differentiable. Around here. It could be continuous at other places. If it isn't continuous around x equals a, then it's not differentiable. Also, if we graph it and it has a sharp corner at that particular point, it's not differentiable. Or if the tangent line there is a vertical line. Remember from your algebra, if it's a vertical line, the slope is undefined. And since you remember the derivative is the slope, if it's undefined, then we don't have a differentiable function. We can't do it. Here's an example. F of x equals 1 over x. If you graph it, take a look at that. Here's your eyes taking a look at it. Notice there's no tangent line at x equals 0, so the limit doesn't exist at x equals 0. Now the derivative does exist, remember, back here, because there are no problems there. It does exist back here. It exists a lot of different places, but not around x equals 0. Next one, we have f of x equals x minus 3 times x cubed. A little bit strange, perhaps, but if you graph it, here's where graphing calculators, it's something you really have to have. Throw that in your calculator, let it do the heavy work. Here's your graph, notice there's a sharp point there. So near that sharp point, it's not differentiable. Out here, it's differentiable. Out here, it's differentiable, but not at x equals 0. Another example, the cube root of x is not differentiable around x equals 0 because in this vicinity, you've got an undefined slope. So continuity at x equals a, how could we define it? Well, it's pretty simple. Remember our limits. We have left-handed limits, we have right-handed limits. If we've got both of those, check for the left-hand limit, check for the right-hand limit. If it equals the function value at a, if all those three are equal, then we've got continuity at x equals a. Just a reminder, continuous functions mean if we're using a pencil to draw our picture, then we can draw it without lifting the pencil from the paper. Continuous on an interval. That means a continuous at every point inside the interval. So for any point, any x value between those two, if it's continuous at all those points from x sub 1 to x sub 2, then it's continuous over the whole interval. Next, use the definition of a derivative to find f prime. So we're looking for f prime of x, alias y prime, alias dy dx. So let's go back to the definition, back to the limit. For the difference quotient, that's step 1. 2 points, we use x, f of x, and x plus h, f of x plus h. So we've got delta y, we've got delta x by subtracting those values from the points. Putting those expressions into the difference quotient. See if I can move this out of the way. Okay. Sorry, I had something in the way. I couldn't see it too easily. So putting them in the difference quotient. Okay. There's our difference. There's our slope. There's our difference quotient. And there it is with x plus h, and the x put into x squared, our function. That's what it looks like. We'll need to expand the x plus h quantity squared. Remember, I told you several times, this is a good one to memorize. Binomials get squared all the time. X squared, h squared, and the middle term is 2 times x times h. So it looks like this. Remember, we're subtracting the x squared, and 2 of those will give us 0. we'll have this left. Remember, don't lose that h in the denominator. Now divide that h into each term in the numerator, or factor it out like this. Those h's cancel out. And this is what we've got for the difference quotient. Step 3, we're going to take the limit of that as h approaches 0, which means we're taking the limit of 2x plus h, which is what our difference quotient is. Since, again, that's a polynomial, so it's going to act nicely for us. Just put the 0 in for the h, and we'll be in good shape. There's our derivative from the definition of a derivative. You can see that no matter where you are on a line of slope y equals x, the slope is 1. You can see some of the results in a table. At x squared, we're going to have a slope of 2x. At x cubed, we'll have a slope of 3x squared. All someone needs to do is tell us what x is, and we can find the slope. Of course, for the first one, it doesn't matter what the x is, the slope will always be 1, or the derivative. Now, if you take a look back there for a second again, look at those slopes alias derivatives. 1, 2x, 3x squared. Look at where they came from. X to 1, x squared to 2x, x cubed to 3x squared. See a pattern? So if that's the case, notice that we also have that derivative. Do you see a pattern? Some of you do, because you've been here before. So then you might think perhaps this would be the derivative for x to the 5th. And here's one of the most powerful things, and one thing that some of you have been waiting for weeks. The power rule. Hooray! The power rule says, if this is our function, x to the n, bring that n out front as a coefficient, or as a factor rather, and reduce the denominator by 1. So n comes out front, and we subtract 1 from the exponent, and that is our derivative. Not all functions are that simple, but many pieces of them are, and that's the beauty of it. Basic rule is, if this is your function, remember y and f of x mean the same thing. And I'm going to go back to using the pen. Now, one thing you might notice is from the power rule, if I rewrite this, y equals mx plus b, m and b are just some numbers. They are not represented by variables. So if you're going to use that rule we had back here, this is x to the first power. So bring this 1 out front. So you have 1 times m, and x, you'll subtract 1 from the exponent, and that becomes a 0. Now, if we write this as x to the 0, that's being a little bit obsessive, but it's true. If you bring that 0 out front, well, 0, b, x, and minus 1, but that 0 is going to make everything there 0. Over here, what do we have? X to 0, or anything to the 0 power pretty much, is 1. So you can replace this part by 1. This is a little bit sloppy, but replace that by 1. So all you've got is m for the slope. So there's another way. You might want to just memorize that. If you've got a line, the slope and the derivative are the same thing. Remember that. Slope, derivative, same thing. Special cases. This is also one of those things where if you don't like memorizing things, this is pretty handy, really. So if you've got something like this, you've got a function equals to some constant. For example, suppose your function value is 7. That's the same thing. Then the derivative of that is just 0. If there's only a constant here, if your function has a constant value, whether it's 7, 18, negative 52, whatever it is, the derivative is going to be 0. If you think of it another way, this is the same thing as y equals 7. You might recognize this as a horizontal line. What's the slope of a horizontal line? 0. Ta-da! Second, if you've got f of x equals x, remember that's x to the 1, so 1 comes out here. So the derivative, bring that 1 out front. There's 1 here already, so 1 times 1 is 1. And x to the 0, because you subtract 1 from the exponent. And what do you get? Well, anything to the 0 power basically is 1, so 1 times 1 is 1. And there you go. If you got just that, if x equals x, then the slope is 1. You might also note that geometrically, the slope would be a 45-degree angle. Might be a good one to remember. Another thing, if our slope is negative 1, then the slope will be negative 45 degrees. By the way, that's the same thing as 315 degrees in case you're obsessive about keeping positive values of the angles. Next, polynomial function. Polynomials are your big friends. Polynomials are differentiable, period. How do you differentiate them? Very easy. First of all these a's represent constants. For the first term, since this is just a constant, your derivative of this part of it is just 0. On the second one, this has an exponent of 1, so you bring the 1 out front. You have a sub 1. This becomes a sub 0, which is 1, and you leave it like that. On the next one, bring that 2 out front. You've got 2 times whatever that a sub 2 is, and your exponent drops to x to the 1, and so on down the line. The last one, you got n a sub n, x to the n minus 1 will be the derivative of the last term. Very nice. Once you got the power rule, you definitely have a lot of power when it comes to differentiating. So here's the general case, which I sort of mentioned earlier. Let's throw in an example here. C represents a constant, so let's use 42 as our constant. And we'll call our function f 42x to the third perhaps, just for practice. What's the derivative of this f of x. Bring that 3 out front. 3 times 42 is, 126x. And reduce that 3 by 1. It's now an x squared. And that's your derivative for 42x to the third. Bring the 3 out front. Multiply it times whatever coefficient is there. Got it? Reduce the first exponent, the exponent for the original function. Reduce that by 1, 3 minus 1, and there's your 2. Next, find the derivative of each of the following functions. Good practice. Can you do this? Hit the pause button if necessary. What is the derivative of this one? Here's one where you can be extremely fast if you remember the derivative of any constant is, got it? 0. No matter what this number is, if it's a constant, the derivative is 0. Here's another one to look at. G of x. Suppose g of x is pi. Pi is a constant. So g prime of x, the derivative of that, is 0. H of x. Suppose that's 74286. What's h of x? Since this is a constant, 0. Very simple. How about 5x cubed? Can you do that? Pause for a second, write down your answer. Don't cheat by just saying something in your head and then changing your mind later. Oh, I meant this. What's the answer? Did you get 15x squared? If so, I'm proud of you. Moving on. Next. We're halfway there. We've got another one. This one has a fraction. We have to have fractions, of course. They are real numbers. But use the rule we had back here. So you can do this one. Pause if necessary. What do you get? Now there is a trick on this one. You follow the rule, you'll be fine. If you don't follow the rule, you might be tripped up. Bring that 1/2 out front of the x, and then subtract the exponent by 1. So the solution is, drum roll someone, there's the 1/2 that I brought out front. The x's exponent becomes 1/2 minus 1, or x to the negative 1/2. A little bit of fraction work here. In fact, before I go on, what's another way of expressing that? First of all, negative exponent means we should take this and put it in the denominator. So we could change that. There's our 1/2 that we've already got. Since this has a negative exponent, we've got x to 1/2 in the denominator. There's another thing we can do though. I'm going to give you the full treatment here. X to the 1/2 is another way of saying square root. So we could say 1/2 square root of x. But I'm not finished, because one of the rules you should have learned a long time ago is that you don't put any kind of root in the denominator. This is not good procedure as an answer. How can you fix that? Well, in this case, since this is the square root, we can do a little bit of algebraic magic like this. Since I'm multiplying by 1, however exotic it is, it's legal. It doesn't change the value of our derivative. What do I have on the top? What I've got on the top now is the square root of x, and on the bottom, because the square root of x times the square root of x is x, There's our proper answer. I bet you didn't get it. Good tip for you though. Next, how about the derivative of g of x? I just gave you almost a tip on this one. Let's see how this goes. G of x is 1 over x. Now what are we going to do? Rewrite it so that it looks like it can be used with the power rule. Remember, this x is in the denominator, which, like that x to the minus 1/2 we had before, bring it up to the other side of the fraction, the other side of the fraction bar, and just change the sign of the exponent. So g of x, the same g of x, can be written like this, which means that for the derivative, we'll bring that -1 out front. Here's our x. And remember, we subtract 1 from the exponent, so what do we get? -2. Now where does that take us? Well, this shouldn't be our final answer because final answers shouldn't have negative exponents. Well, negative exponents means move it to the other side, so our derivative, g prime of x, would be negative. The 1 is a regular 1, but this becomes x squared on the bottom. You got that? See if you can do it the next time. Okay. Now this is just another way of saying take the derivative of h of x with respect to x. So h of x equals this. You might guess that we're going to move this x to the 2/3 up to the top. So the way we're going to write it is like this. That's the way we can use the power rule. So h prime of x, you'll leave that 18 where it is, but you bring the -2/3 out front and multiply it times the 18. And then subtract 1 from the -2/3. So here's our derivative, another way of describing it. Another way we could say dh dx. It's another way of saying the same thing. So that's what we're taking the derivative of. Here's our 18 that was there to begin with. Bring the -2/3 out front to multiply it times the 18. Reduce the exponent by 1. In other words, subtract 1 from the exponent. And we'll get something that looks like this. A little bit of cleanup here. So the -18 times 2 over 3 reduces to a -12, and we've got x to the -5/3. We could change this a little bit. We'll leave it for the time being. Constant times the function rule. We've actually used this. So when we have a number outside the function, we can just take the derivative of this, and when we're finished with taking the derivative of this, multiply it times whatever this constant was, and we've got the derivative for whatever our function was. Some real simple ones. If we've got a function that is several terms long, we can just take the derivative of the individual pieces, keep the pluses or minuses between the pieces, and put it all together in our answer. So here's a warm-up. Can you do this one? Bring that 2 out front, multiply the 5 times the 2, reduce the 2 by 1, and And there's your answer. Next, when you do this one, remember the derivative of just the x alone is a 1. If you remember that shortcut, it's not necessary, but it's handy. If you remember the derivative of this is 1, and the derivative of y prime will be just negative 4 times 1. There's negative 4 that was there before. Bring the 1 out front. Reduce the exponent by 1. X to the 0 is 1. So our derivative is negative 4. Next, pause and see if you can do this by yourself. We just did these separately. You should be able to do this. You'll take the derivative of 5x squared. You'll take the derivative of negative 4x. And basically you just paste them together into the derivative function. Split them up like this. Divide and conquer. You got the original ones, or you can find them again. That's good practice. There's your answer. There's your derivative of the function 5x squared minus 4x. Okay, a little more interesting. Can you do this one? I dare you to pause the video and do this one. If you need a hint, here's a hint for you. Sometimes rewriting makes a big difference. X cubed, that looks like it's ready. That's no problem. How about this square root of x? Rewrite it as x to the 1/2, and then it's ready for the power rule. Anytime you can switch something so you can use the power rule, you're in business. And the last one, you've seen this before. That x in the denominator becomes x to the minus 1. Then you're ready for the power rule. Here's your rewrite. Split them up. Take the derivative of each of the terms. Do the work. Clean it up a little bit. And 2 versions of your answer. The first one is good. The second one is better. In fact, even this could be improved a slight bit, but let's not be too picky at this point. How about this one? Algebraic manipulations. This could prove handy at some point. Trust me on this one. So, u is your variable. So, one of the implications of this is you're not going to be stuck on using x all the time. You can use other variables. T, for example, for time. So first of all, we'll write it out, multiply it out. Remember, when you multiply this times this, since they're both u's, you add the exponents. So 2 plus 1/2 for the first one. And for the second one, you'll be adding 1 plus 1/2. Those are the u exponents that you're multiplying together. And 2 is the constant. So there's your simplification. It's ready for taking the derivative using the power function. So what's next? We're going to take the derivative of that. We're going to split it up, take them one piece at a time. You don't really have to write those separately, but that's what you're going to do in your head. Bring that 5/2 out front, reduce the exponent by 1. On the other one, bring the 3/2 out front, reduce the exponent by 1. A little bit of cleanup work, and there is your derivative. And you could change those using square roots, but The idea is to get familiar with using the power rule. Okay, this gets a little bit more interesting, doesn't it? But a rewrite can make a big difference on this one. Several weeks down the line, you'll have the quotient rule. Well, maybe not weeks. You could do this with something called the quotient rule. However, not so fast. You can actually do this without any quotient rule. So there's the original function. A bit of a rewrite. Another rewrite because that v to the 1/2 gets distributed as a divisor across the two terms in the numerator. Take those individually. What do you get? V to the 3/2 plus v to the negative 1/2. Now it's time to take the derivative. Three halves out front, reduce the v's exponent by 1. The negative 1/2 out front, reduce that negative 1/2 by 1. Remember that you were taking 1 away from negative 1/2, so you have negative 3/2. A little bit of fractional work, just to see if you can do that. And we could factor it. We could write it like this, which could end up being that. Right now, if you can get this, you're in great shape. Tangent lines. Tangent lines, if we consider a curve like this, a tangent line here would look something like that. If we know what x we're interested in, we can take the derivative and then put that x value in there to get the slope. With that slope, we can actually find the tangent line. So, first, find the slope of the tangent line at 2 points, x equals 4, or x equals 2 and x equals 4, and x equals 5. So first, find the derivative because that's going to be your slope, your general slope at any point. So there's some of your work to get the slope for that. A little bit of cleanup work on that. Now, we've got some points. We're going to find the slope of the tangent line at each of those points. For x equals 2, put the 2 in for the x there, and you get a slope of 4 where x equals 2. Slope equals 4 where x equals 2. Next, all you have to do is put that 4, put it in for that x, and you can find the slope. Where x equals 4, slope equals 0. At x equals 5, put the 5 in for this x, and you get a slope of negative 2, where x equals 5. Now find the equation of the tangent lines at each of those points. Use the point-slope form, and there's the point-slope form. I think I mentioned a couple weeks ago. This can be very handy. The derivative is going to give us the slope, and we're given some points. We're given x values for the point. We can use the function to tell us what the y is that goes along with that x. That gives us a point, x sub 1, y sub 1. Use that with the slope, and you can write the equation. So at x equals 2, x value is 2. Where that x value is 2, the y value is 12. So we know one point is 2, 12, and we want the tangent line at that point. Well, we know that the slope there is a 4, so putting that into the point and slope form, we've got the equation before we cleaned up. Just put those numbers in, and there's the equation of the first tangent line. The tangent line of x equals 2. Another one, x equals 4. We've got another point. We want the tangent line at that one. X equals 4. Put that into the function. And so our second point is 4, 8. Here's the 8. And from part A, we know that the slope there is 0. So we use the point slope form again. And just put the numbers in. And we get y equals 16 is the equation of the tangent line at x equals 4. This one. At x equals 4, that's the equation of the tangent line. One more time. At x equals 5. Take that 5, put it in the function, you get a y value of 15. So you've got a point, 5, 15. You've also got a slope that we already found with -2. And go to your point slope form again. What do we have? Put the numbers in, a little bit of cleanup work. There's your equation for the tangent line at x equals 5. There's a picture of all of that we did with the tangent lines and the equations of the tangent lines. You might want to actually graph that parabola yourself. Take this, put it in your calculator, and graph it. If you're a little bit more industrious, what you could do is you could graph these 3 lines that you found. Graph this one, and you can see how it shows up over here. Graph the second one, y equals 16. You'll see that it shows up here. And graph this one, you'll see that it's tangent on the right side. It's not very hard, and it's a nice reminder of how all of this fits together. Remember, derivatives are slopes. Slopes are derivatives. Of course, we can't go too far without having a little bit of a physical example, and we've got one here. We've got a sailboat, and this has nothing to do with my name being a sailor. Besides, that's not where my name came from. My name came from either German or Swiss origin, and it actually means rope maker. Imagine that. The spelling was different too. So we've got a sailboat, and we've got a period of 5 minutes. That should remind you of average velocity, remember? Because we've got a period of 5 minutes. To travel a distance from a starting point according to the function, so you've got s of t, s represents the distance, t represents time, this is a reminder, and note also the time is in minutes, you might need that, and the distance is in meters. So when we get our answer, make sure you use meters and minutes. So how fast is the boat moving at the starting point? So you'll start with s of t equals t cubed plus 60t. Starting point. Okay, starting point. First of all, what's the time? 0. How fast is it going? That's a slope. That's a rate. Derivative. So what we need is s prime of t. And here's a chance to do some derivatives. Pause it, see if you can do it. Come back. All right, you back? So we'll bring the 3 out front. Subtract the exponent by 1, 3t squared, plus. Now this is a constant times t. The derivative of this part is just a 1. So there's our derivative for s of t. Now we're talking about t equals 0 at the starting point. So what's s prime, or what is the speed of the boat at t equals 0? 3t squared. We're using a t of 0. Notice what I did? I just put the 0 in for t. What do I get? 60. 60 what? You know already that I'm a little bit of a stickler for units. 60 what? It says how fast is the boat moving? Well, fast, sort of like miles per hour. So this is what we're accustomed to, but instead of miles, we're using meters. Instead of hours, we're using minutes. So at the very start, we're going 60 meters per minute. I'll let you figure out whether that's fast or slow. Second, how fast is the boat moving at the end of 3 minutes? All we need to do is take this. We've already got s of t. It's right above here. At 3 minutes, we'll put the 3 in for the time. Remember, that's 3t squared for the derivative, plus 60. So 3 times 9 is 27, plus 60. And our answer is 87. And remember, we need the units. You've already got the units. So it'll be meters per minute. And you can also tell that the boat is speeding up. It's not slowing down. So how well did you do? Or at least did you follow it? There's your velocity, which is the derivative of the distance function. You might want to keep that in mind. There's the derivative at the starting point, t is 0. So you put 0 in for s prime. There's 60 meters per minute. Part 2, at 3 minutes, put the 3 in for s prime. What do you get? 87 meters per minute. How do you do? All right, last of all, let's wrap it up with some relatively simple ones. Which of the following might be the derivative at a point? Could these be derivatives at a point? Remember, derivatives are slopes. Oops. This is oversimplified, but I want you to get the idea. Derivatives, slopes. Rates. We're all talking about the same thing. So, on the first one, could this be represented by a derivative? Is it a slope? Is it a rate? You got your answer down? Part B, fish per day. Could that be a derivative? C, 23 ears of corn. Could that be a derivative? And last, put your answers down. 19 neutrons per millisecond, excuse me. Could that be a derivative at a point? You got your answers down? Let's check it out. First of all, miles per hour is a rate of change, therefore it's a possible derivative. Part 2, fish per day, also a rate of change. 3, 23 ears of corn. It's a quantity but not a rate. Nothing's changing. Derivatives, calculus, it's all about change. Remember that. Part D, 19 neutrons per millisecond. It's a rate of change. Two things you might notice, not exclusively because there are other kinds, but you see the per, see the time, those are dead giveaways. 19 neutrons per millisecond. Okay, well I guess we're at the end, and I'll have to say goodbye. I'll see you next time.